Okay, so this is a short video recorded by Dr. Shan to show you how to conduct hypothesis test when there are two populations involved and also ANOVA. Okay, first let's look at an example where we calculate the difference, hypothesis test, the difference between two population means when sigma 1 and sigma 2 are unknown. Okay, so here is the example about the mileage per gallon for two cars. Okay, so if you go to MINITAB, go to stat, one basic stat statistics. This time you go to two sample T. Okay, because we have two populations and we don't know the standard deviation, population standard deviation. Therefore, we need to use T. Okay, so you can, if you have the raw data, you can choose, for example, in a column. Now we will use the summarized data here. The sample size, okay. Let's go back to see it. Okay, so one is 24, and another is 28, and the mileage per hour, one is 29.8, one is 29.8, one is 27.3, and then standard deviation. Okay, it's a 2.56, 1.81, 2.56, 1.81. Okay, so you can go to option. Now here it lets you to choose the alpha level, so we will do not change it. It's still 95, and the hypothesized difference is 0. Okay, so we need to change the alternative hypothesis to difference greater than hypothesized mean. Okay, then hit OK. Okay. Look for the output. Okay, so here is the output. So we can see the method is comparing to the difference between two population mean, and the sample we can verify the data inputs, and then the difference between the two sample average is 2.5, and the lower bound, because this is one-sided test, 95% lower bound is 1.448, so it does not include 0, so we reject the null hypothesis. Okay, and also the t-value is 4, degree of freedom is 40, p-value is close to 0, less than 5%, so we reject the null hypothesis, and this is consistent with our manual calculation. Thank you. Look at ANOVA. Okay, so you can enter the data manually, or you open the file that I have for you. So if you go to, okay, so plant. So here is the data. You have working hour, right? And then you have 3 plant. Okay, so go to stat, ANOVA, one way. Okay, so the response should be work hour, and the factor is plant. Okay, so you can see options, right? So okay, so we do not change anything, and then we hit OK. Okay, so here is our one-way ANOVA test. You can see here is the interval plot. You can see there seems to be a effect for the plant 2, and managers in plant 2 work longer than plant 1 and plant 3. However, let's look at some numerical answers. Okay, so you look at one-way ANOVA output. So the null hypothesis is all means are equal. The alternative hypothesis not all of them are equal. Okay, so the plant has 3 levels, 1, 2, 3. Now if you look at the analysis of variance, you can see the plant have 2 degrees of freedom, which is we have 3 plant, 3 minus 1 is 2, and the F value is 9.55, so the corresponding p-value is 0.003, so it's less than 5%. We reject null hypotheses. We're saying that not all means are equal to each other. Okay. So now let's take a look at the two-way ANOVA. Okay. So if you can open the zooplankton. Okay, so first you look at the data. Okay, so you can see that we have 12 measures. The first column corresponding to number of zooplankton, the second one corresponding to the supplements. We have 3 levels. The third column corresponding to lake. The reason we have 12 data points is because we have 3 supplement level and 2 lakes, and for each we will take 2 measures, 2 samples. Okay, then you go to stat ANOVA, balanced ANOVA. Okay, so and then the response parameter should be zooplankton and the model. Okay, so the model is all the terms that you think have effect. So supplement and double click lake. Now to represent interaction, you need to have supplement again and then times the lake. Okay, so we have 3 terms, one corresponding to main effect of supplement, one corresponding to main effect of lake, and then one corresponding to the interactions. Okay, so you hit OK. Now here is the outcome. You can verify the factor information. You have 3 level for supplement and the 2 lakes, Dennison and Rosie. And okay, so for the analysis of variance, you can see the first row corresponding to supplement, and the F value is 9.25, corresponding P value is less than 5%. So we rejected the null hypothesis. We will say that the supplement does have an effect. Now for the second row, the lake, the ZF statistics is 0.21, corresponding p-value is 0.666. We see that it's greater than 5, so we fail to reject the null hypothesis. So we conclude that lake don't have effect. And then the interaction, supplement times interact with lake, and we can see the F statistics is 2.71, corresponding p-value is 0.145, which is greater than 5%. So again, we reject the null hypothesis. We will conclude that there's no interaction effect between supplement and lake. Okay, so I think now if you go back to the gauge INR study, sorry, I forgot. You can also plot the main effect. You go to ANOVA, go to the main effect plot. Okay, so the response is zooplankton. Factor could be supplement, for example. Okay, so you can see the supplement does have an effect. The supplement 2 seem to have the highest effect as compared to the other 2. Okay. Now you can also look at the ANOVA main effect, look at the effect of lake. Okay, it seems that there's some effect of the lake. However, this is just a visual display, and also the output, the numerical output, we should always check for p-value and the p-value. And the p-value said it's not significant, so there's no significant lake effect on the counts of zooplankton. Okay, so you can also look at the interaction plot. Go to ANOVA, interaction plot, and then okay. So again, the response is zooplankton. Now for factors, let's delete this and double-click supplement, double-click lake. and then click OK. So now you can see the interaction plot. Again, from the plot itself suggests that there might be an interaction effect because all the three lines do not parallel to each other. So the way to interpret this seems that the supplement 2 has a larger effect if the zooplankton is from Rosie Lake as compared to Lake Dennison's. However, you should always check for the p-value to see whether it's statistical significance or not, and recall that the p-value is less than 5%. It is greater than 5%. So we do not conclude we conclude there's no interaction effect. Okay, thank you. So let's go back to gauge R&R study. So open the data. Okay, go to gauge AIAG.example. You see the 3 plans. Sorry, it is 10 parts and 3 operators and the measurements. Okay, so you go to Stat, Quality Tool, Gauge Study. Remember, we are using a cross design. Okay, so the part is parts, operator is operator, measurement is measure, and we leave the method as ANOVA. So we hit OK. So we already saw this figure here. So here we are ready to interpret the interaction plot. There does not seem to be a significant interaction effect because all 3 lines are there parallel to each other. Okay. Now if you look at the output, last time we skipped the ANOVA part, we focus on the gauge R&R, but now we can take a look at the ANOVA part. We see that part have a F value 492.29, and the corresponding p-value is less than 5%. So we claim the part is significant, and then operator has a very small p-value, and then we said it's also significant, and the interaction between part and operator is 0.974, which is greater than 5%, and we conclude there's no interaction effect. Okay, so the second table it considered the two-way ANOVA without interaction because we already found that there's no interaction, so we redo the study again, and we found that the parts, the p-value is still less than 5%, and also the operator is less than 5%. So we conclude that part is significant and the effect of operator is also significant. Now recall that to check the output for gauge R&R, we say that if the percent contribution is less than 1, it's definitely acceptable. If it's between 1% and 9%, we said it might be acceptable, which is this case here. Okay, so this concludes the video, and again, if you have any questions, please let me and the TA know. Thank you.